Hello, this is Arif Ahmed Siddiqui from Chemical Department and Group 10. This is my ELP101 project and the topic is transformers. Introduction to the topic. The transformer is an electrical device designed on the basis of the concept of magnetic coupling, or you can say mutual inductance. It uses magnetically coupled coils to transfer energy from one circuit to another. Transformers are key circuit elements. They are used in power systems for stepping up or stepping down AC voltages or currents. They are used in electronic circuits such as radio and television receivers for such purposes as impedance matching, isolating one part of a circuit from another, and again for stepping up or down AC voltages and currents. Too much for the introduction slide? Right. Now let's dive into the topics or the concepts that are involved in the transformer. That is mutual inductance. Now, when two inductors are in close proximity to each other, the magnetic flux caused by current in one coil links with the other coil, thereby inducing voltage in the latter. This phenomena is what is known as mutual inductance. Now, let us first consider a single inductor, a coil with N turns. When current I flows through the coil, a magnetic flux phi is produced around it. Well, according to Faraday's law, the voltage V induced on the coil is proportional to the number of turns N and the time rate of change of magnetic flux phi. That is, V is N d phi by dt. On simplification, we can get V is L di by dt, where L is a coefficient of inductance. Now, just extending the same to two coils that are mutually or inductively coupled. Well, we have V1 as N1 d phi1 by dt or L1 d I1 by dt and V2 as N2 d phi12 by dt. That is the flux from of 1 with respect to 2, and that V2 can be equated to M21 d I1 by dt. That is, the voltage in the second coil is somewhat linked from the first one, and that here M21 is the coefficient of mutual inductance of second coil with respect to the first. And the same can be applied to the second case in which we have a current in the secondary coil and not in the primary one. That is, V1 can be said to be equal to N1 d phi2 by dt. Phi2, yes, phi2 is the flux from the second coil that is linked with the first one, and that can be, and V2 can be equated to N2 d phi21 by dt is equal to M12 di2 by dt, where M12 here is the coefficient of magnetic induction or mutual induction of the first coil with respect to the second. And a clear observation that we can observe is that M21 is equal to M12. Now extending or applying the topics to transformers. Well, transformers. Electrical transformers are machines that transfer electricity from one circuit to another with changing voltage level but no frequency change. And let us see the working of the same. Well, a transformer's physical basis lies in the mutual inductance between two circuits that are linked by a common magnetic flux. It is usually equipped with two windings, primary and secondary. These windings share a magnetic core that is laminated, and the mutual inductance that takes place between these circuits helps transferring electricity from one point to another. Well, depending on the amount of linked flux between the primary and secondary windings, there will be different rates of change in flux linkage. To ensure maximum flux linkage, that is maximum flux passing through and linking to the secondary winding coil, a low reluctance path is placed common to both windings. This leads to greater efficiency in working performance and forms the core of the transformer. And the application of alternating voltage to the windings in the primary side creates an alternating flux in the core. This links both windings to induce EMF in the primary as well as the secondary side. EMF in the secondary winding causes a current known as load current if there is a load connection to this secondary section. This is how electrical transformers deliver AC power from one circuit to another through the conversion of electrical energy from one value to the other, changing the voltage level, but yes, does not change the frequency of the current. Let us see some classifications of transformers. And a first classification can be on the basis of design, and we can classify transformers into core type transformer, which this transformer that features two horizontal sections with two vertical limbs and a rectangular core with a magnetic circuit. Cylindrical coils are placed on the central limb of the type transformers. And the second one is shell type transformer that has a double magnetic circuit and a central limb with two outer limbs. And a second classification can be on the basis of purpose, and that we have step up transformer and the step down transformers. From the raised diagram, it is clear that step up transformer that has greater number of turns in the primary side, and it means that the voltage will correspond to that which forms the base of a step up transformer. And the step down transformer that has greater number of turns in the primary section, and then we see that the voltage in the secondary one is lesser. Some uses of transformer. The major uses of electrical transformer include raising or lowering the voltage level in the circuit of an AC, increasing or decreasing the value of an inductor or capacitor in an AC circuit, preventing the passage of DC from one circuit to another, isolating two electrical circuits, stepping up the voltage level at the site of power generation before the transmission and distribution can take place. Common applications of an electrical transformer include pumping stations, railways, industries, commercial establishments, windmills, and power generation units.